Hello, everyone. Mr. Hein, and now we are starting chapter 5. And at the beginning of this chapter, we're just going to be relating it back to how a position, velocity, and acceleration relate, which hopefully at this point you feel like you have some sort of idea, and hopefully this just cements it for you. So we're going to look at it through two examples here, which will help with your problems in the assignment for this. So the first example here is, say we have a position of an object follows the data seen below, where at these times that's the height of the object, and the object was thrown up and it's traveling back down. Okay. Now, notice that there's two roots here at 0, 0 and at 4, 0. So I know that the function is going to be x and x minus 4 to represent the two zeros. And then we need to consider the stretch factor a. So we plug in any of the other points. I'll plug in 148 here, since those are the smallest. And what I get here is that 48 will equal a times -3, in which a is equal to 48 divided by -3, which is -16. So that means that the position function, which I'm going to call d of t, can be related as d of t is equal to -16. And I guess it shouldn't have been x, it should have been t, but we can do that now, as follows. So that's the position at any time. All right, so that's the position function. Now, if we wanted to find the rate at which this is changing, so if we wanted to find the derivative of d of t, what would that give us? Well, the rate at which it's changing would be its rate in height. It's how it's changing in feet per second, which feet per second you can think about as the velocity function, right? So the derivative of position, the derivative / rate of change of a position function is a velocity function. And hopefully that's not totally new to you, because we've been seeing that all year long, but hopefully it makes a little bit more sense these days, where, okay, we take the derivative of this to get velocity. Well, that will be, I'm going to rewrite this up here before I take the derivative as -16t squared plus 64t. It'll just be easier for us to apply the derivative to that. So then we'll get -32t plus 64. So that there's our velocity function. And then if we were to take the derivative of this, the derivative of a velocity function, what do you get? Well, you end up getting the rate at which velocity is changing, which is the acceleration as a function. So then a of t will equal the derivative of the velocity function, which is just -32. Which, what's fascinating about that is, if in units here, the velocity is feet per second, and the acceleration, this -32, is feet per second per second. It's how the velocity is changing, right? The change in velocity over the change in time, which feet per second you could also write as feet per second squared. But what is -32 feet per second? Well, any of you have taken physics, well, that is the constant rate, the universal rate of gravity. Well, that's gravity. So what's interesting about this is applying this to physics. Just as we went from position to velocity to acceleration in this order, we could actually work backwards in the same order. We can also go in the opposite direction. So say, for example, we know that on Earth, gravity is -32 feet per second squared. So if we start with the acceleration function of -32, well, if we wanted to get the velocity, if we worked backwards, well, notice derivative gives us the rate. If we want to work backwards, we can use the antiderivative, which we can use the sign of the integral. So if we take the integral of -32, the antiderivative of a of t, we end up getting the velocity function, which would be -32t plus c. And now what's c represent here? Well, c is your initial velocity. Or it might be, whatever you're at at v of 0, because if you plug in 0, you obviously have c. Which, say for our problem, let's say your initial velocity is 10 for purposes of being able to find the next function. So we're going to say v of t is negative 32t plus 10 in our case. Now, if we wanted to find the position function, we work backwards again. So instead of taking the derivative, we take the antiderivative. So then the antiderivative of v of t is going to give us the position function v of t, which is negative, which would be t squared over 2, which implies to negative 16t squared plus 10t plus c. Well, now that c represents your initial position at v of 0. So let's say that, for example, our initial position is 20. Well, then our equation would have been, running out of room here, and I'm going to squeeze it on here. It would have been d of t equals negative 16t squared plus 10t plus c. So that's great. So now with derivatives and antiderivatives, we can actually work between all three of these: derivative, acceleration, and velocity. And here's a graphic to summarize it. So in summary, if you have a position function and you want to study its rate, which is velocity, and you want to study that rate, which is acceleration, well, to get from position to velocity, we would take the derivative of position. And to get from velocity to acceleration, we would take the derivative of velocity. Or you can even think about it, if you want to go straight from position to acceleration, well, since there's two derivatives, you could say it's the second derivative of your position function. And just like how we can work one way, we can work backwards as well. So the idea is if you want to go, if you have the acceleration, you want velocity, well, opposite of derivative, thanks to the fundamental theorem of calculus, is we would do the antiderivative. Just like the opposite of multiplication is division, and then we would take the antiderivative to work back to that. And there you go. So it's almost like, here's another graphic to help you see this. If you have d of t, v of t, and a of t, well, v of t can be represented by doing the derivative. Well, we can even write it like this. We can write it as d prime of t, the velocity, or the derivative of the position function, and we could write acceleration as v prime of t, the derivative of velocity. And what I was saying here with the second derivative is acceleration is also the second derivative of your position function, v of t. And if we want to work backwards, the second part here in red, you have your functions d of t, v of t, and a of t. Well, to get v of t, that's just the integral of a of t to get the antiderivative. And then to get the position function, what's the antiderivative of your velocity function? Or getting a little bit more advanced, this is not in our class, you could do, it's the second antiderivative or integral of a of t. So different ways to think about it, but hopefully now you're at a point where we can navigate between these three just given one of them. And if you've taken physics before, hopefully this is a nice refresher, or maybe it's all clicked at this point. Hope that helps. Email me, come to office hours if there's anything I can clear up. All right, bye-bye.